Hello and welcome to this design practice 2 module 2. We had been discussing about the utility of product design and how it is important to lay out different forms and shapes, so that it can basically all merge out to be at least the aesthetic form of the product that we are envisioning. It's a very important process in design to be able to sketch and envision what idea you conceive behind a product. So, this lecture is dedicated to learning a little more of the back-end processing which is involved in tools like CAD, and what is the utility of CAD and how CAD came into existence and how CAD is continuing through. But the involvement here is more related to how you can actually help to scale up, translate, rotate different objects in space by using coordinate geometry. And so, this is the back-end computation which is needed by any CAD design engineer who is actually designing a CAD platform to know about how to handle different shapes on a 2D screen. So, if you look at this computer aided design, obviously a large number of factors are responsible for success or failure related to engineering organizations. And obviously, the most important, particularly when we are talking about engineering products, is the engineering design of products and processes. So, this is one of the key elements for ensuring that an organization is successful. And in order to realize a producible product design, the understanding of the design process necessitates the use of this very flexible computer aided design tool or CAD tool, as we popularly know of. So, it is a way to represent or re-represent in many forms the basic shape or geometry associated with an engineering part, or maybe even a total product. So, computer graphics play an important role in product development and process by generating, presenting and manipulating the geometric models. And if I looked at that design process, and this I think I had extensively done in product design 1, design practice 1 course. There are different steps involved in any designing activity, which starts from the need finding or the problem identification step, the preliminary ideas step, the refinement process, the analysis process, decision process, and finally implementation, which is all visible here as a sort of a algorithm. Okay. So, interaction with customers is more or less the reason why a problem can be identified or it comes up, and then there are various steps which actually lead to the defining of a solution and then evaluating the solution, and so if it is found okay, then implementing the solution. So, I am not going to delve into the details of this process because this has been taken up in design practice 1, but what is important here is a lot of these steps do involve ideation and sketching, and a lot of these steps are involving the feel and touch of a product, for which the necessity of using powerful CAD tools automatically come into existence. So, if I wanted to just see how CAD developed over the years, how it started, really the origin can be traced back to almost 1963, when a system called Sketchpad was developed. Okay, the system was known as Sketchpad. It is now known as interactive graphics. It was developed under again a defense project which was subcontracted, and this was also known as the semi-automatic ground environment project or SAGE project. And what it essentially helped in doing is to help change the radar information into computer integrated pictures, and that is how the CAD technology, the modern day CAD technology so far evolved. So, it allowed the flexibility of choosing the information by pointing a light pen, so that you could zoom up into a certain region, go into the details, so on and so forth. And the issue was about at what resolution you could save the picture, so that you could reflect all those details come up as and when you pinpointed or indicated a certain area. So, the interaction of this light pen was typically with a cathode ray tube which would display the image and then help it to zoom up or zoom down and go to different sections of the particular image. So, that is how CAD started. Today CAD CAM systems are almost always round. They are currently available in many forms, many shapes. So, if I looked at overall how a CAD system is placed, it has three major components. One is of course the hardware part, which includes the basic mother computer which does all the computation, and in fact the algorithms or logic that we will be preparing is for this computer to handle various geometries and manipulate various geometries. There are also input output devices or systems associated with the computer. There is an application software which is in place, and then there is an operating system software. So, these are the three essential components, ingredients of a CAD system, which would help you to handle a lot of data, do a representational form of the data, and then do data manipulation based on change in representation, so that it could be transported back as data and stored into the database of the CAD system. So, typically the operating system, as I think all of us are aware, it is a software which acts as an interface between the hardware and the CAD application software system, and this right here. And if we wanted to look at some of the classification schemes or the basis of classifying the various CAD/CAM systems which are available, they are really based on the types of the host computer that drives. There can be mainframe based systems, for example, there can be mini computer based systems, there can be workstations, and then there can be microcomputer based systems. So, these are a broad set of classifications which can come handy when we talk about different CAD/CAM systems. And a very important backend computational aspect of all these is how you are taking data and representing and re-representing and manipulating, so that there can be a data input output to give different orientations, different geometries, different shapes, forms, etc., within the RAM space of a CAD system. So, this topic of geometric transformation is really indicative of such data handling and manipulation, and it kind of gives you an essence of or a connect between the actual graphic display which is there on such a system with numeric data which is being processed by the processor of a computer. So, computer graphics play a very, very important role. No need to mention this in the product development process, and what we really need to do with computer graphics is to be able to generate, present, manipulate different ideas, okay, so that it goes towards that intended solution which satisfies the need of a customer. And so, there are different geometric models which are used off and on for doing this on a very fast basis. So, during the product development process, for proper understanding of designs, it is necessary not only to generate geometric models of the objects, but also to perform manipulations on these objects, so that they can be able to be watched in different views through rotation, for example, or translation or scaling effects, or so on and so forth. And in order to do this, usually the numerical data which is generated by computer at a very high speed is hard to interpret unless a representational mode is used to represent the data in form of a geometry. Okay. And so, as the geometry changes, obviously the back and forth basis, the numeric data also should change, for which organized algorithms should be in place. So, let us look at some of those algorithms which play an important role in determining the data when a certain graphic is manipulated on the computer screen. And if I looked at the basic algorithm of doing such a transformation, we would rather prefer to have first a simpler representation on a 2D mode, and then translate this into the 3D space, so that you could have even 3D forms, shapes being incorporated within the CAD system. So, the first transformation that I will work out here is for the simplest possible activity, which is about translating of objects in 2-dimensional spaces. So, let us say we had a point x, y in a coordinate system, which I am laying out here. So, you have a 2-dimensional coordinate system, and there is a point A somewhere in space which is read by a coordinate x and y, and you want to take this point to another place A dash read by a coordinate x dash and y dash. So, obviously there is a movement along the x and there is also a movement along the y which leads the point to move from A to A dash, and there should be an organized way of representing it in terms of numbers, which is very easy for a processor to handle, which would give you an outcome in terms of what you call translation. So, if I wanted to call this a vector v x y, and this is another vector, let us say v dash x dash y dash. So, I would be able to write this translation in terms of the vector v dash, which is given by the coordinates x dash y dash, equals the vector v, which is actually given, or you can interpret this as the matrix x y plus a certain distance matrix, which means how much the point has moved in the x direction and the y direction. So, let us say if this point is moved by distances dx and dy in the x and y direction, which typically means that this right here is dy, and similarly this right here is dx. So, I have a vector equation now v dash in place, which is equal to v plus d, which shows the effect of translation on the point vector v, okay, which is point A, when it translates to the vector v dash point A dash. So, this is a very simple way of expressing translation. So, x dash becomes equal to x plus dx, y dash becomes equal to y plus dy, and obviously this is only one point, but when it comes to a set of points, for example, if we are looking at a triangular form or shape, or we are looking at a rectangular form or shape, it is defined by more than one points, and so typically all of them would execute similar kind of translational efforts, so that the new coordinate can be quickly computed on the basis of what the old coordinates were. So, this is one very elementary form of translation. D, of course, can be recorded as a distance vector, and this distance vector is again written as the complement. So, it can be used as dx dy transpose, and we can apply this to again a set of points. For example, if I were to consider a triangle which is an array of 3 points, let us say there is a triangle placed at a, b, c location coordinates with respect to this xy plane, and it moves to a point a dash, b dash, c dash by virtue of a translation of the centroid of the triangle, which was initially at xy to x dash y dash, where the centroid translates to a differential distance corresponding to dx and dy. What is important to be seen here, or the aspect that is important to be seen here, is that really after this translation is the relative distance between a and b or b and c going to change because of such an effort. So, in this particular figure we are mentioning the different coordinates a, b, c as 1, 3, 4, 5 and 5, 3.5, and the distance vector is 7 minus 2 transpose, and we would like to find whether the shape or size of the triangle changes because of this translation effort. So, for doing it, let us compute. So, we are using this equation v equal to, or v dash equal to v plus d, and we will do this for all the different points. So, the points x a dash y a dash get translated from the point x a y a through the transpose of the distance vector, which in this case is 7 minus 2. So, obviously, this being given as 1 and 3, okay, would translate to the v dash vector x a dash being equal to 8 and 1. Okay. Similarly, for the point B, the new position x b dash y b dash is represented as x b y b plus 7 minus 2. So, this becomes equal to 11 3, because obviously x b and y b are in as written in the questions 4 5, and similarly x c dash y c dash becomes equal to x c y c 5 3.5 plus 7 minus 2 gives equal to 12 and 1.5. So, if I were to look at the distances a b, b c or c d and whether they change or not, and the value a b could be written as x a minus x b square plus y a minus y b square. This indicates the distance between the points A and B, and this comes out to be equal to 1 minus 4 square plus 3 minus 5 square, in other words root of 13, and similarly a dash b dash equals to 8 minus 11 square, the new values, plus 1 minus 3 square, which again becomes equal to root of 13. So, we see that the distances a b and a dash b dash are not changing. Similarly, you could find out for yourself that b c and b dash c dash also do not change, they are together root of 3.25, or c a and c dash a dash again root of 16.25. So, these are the different numbers in terms of the distances, and so as the distances do not change, the triangular shape or the orientation also does not change as it moves in the translational matrix, or as it moves using the translational matrix. So, that is how you could define the process of translation. We also have another scaling process, which basically would mean that you are stretching the points to a certain extent. Let us say if I say that the distance were d between 2 points A and B in space, now it has become 3d or 4d. That means you are stretching the whole line to almost 3 times the length, and obviously if there are a set of lines which are describing a surface which is actually the the basis of a shape, then obviously if the stretch of a line happens, the shape would also like to stretch to that particular dimension, and we want to find out whether the shape changes because of that. Okay. And so, in order to do that, let us formulate a matrix just as we did for the translational effort. What would happen if such kind of a stretching is done? Is called scaling, and scaling of course can be done because we are talking about a 2-dimensional plane, in terms of scaling towards the x axis and the y axis. Typically, if the aspect ratio were locked to be 1, then the scaling effort would have a single scale. Okay. But otherwise you could have differential scaling along the x and the y planes as well. So, let us say we are talking about a generic form of differential scaling along both directions, and we have a certain point having x coordinate of x, let us say small x, let us say scaled up by a factor Sx. So, we can say that x dash should be equal to Sx into x, and y dash should be equal to Sy into y. In other words, we are restricting ourselves to not having scales similar in the x and y direction, and basically what it means is that we are taking the point x dash in the x axis to another point which is about Sx times away from the point x dash, or from the point x, and we are taking y dash to a point along the y axis which is about Sy times away from the point y. So, if I were to look at a simpler way of representing in terms of linear algebra, the x dash y dash in this case could be represented as a scaling matrix Sx 0 0 Sy times of x and y. So, obviously the result of this would be Sx times of x plus 0 times of y, as conventionally the matrix multiplication is done, and Sy times of y plus 0 times of x. Okay. So, this again same as Sx x and Sy y. Okay. So, this is how x dash and y dash are defined in this particular matrix, and so I can say that the scaling can be expressed in vector form as v dash equals the scaling matrix S times of v, or x dash y dash equals Sx 0 0 Sy times of xy. Okay. Sx and Sy are the scale coefficients in the x and y directions. Let us look at really whether such a scaling event or transformation, if happening to a certain shape, would really scale up the length to as many times as the scale factor. the example on the right here shows that there is a length of a otherwise pentagonal object. The side AB shows the initial length, and let us say this object is now scaled up to about 3 times in size, and the side A dash B dash shows the scaled length AB by just using the scaling transformation matrix, and we can find out what is A dash or coordinate of A dash with respect to A or B dash with respect to B, and we can find out really whether the length changed to so many times as the scale factor was in this particular case. So, the factor in this case is 3. Let us assign some coordinates here to A and B. So, let us have the coordinate of A as A1 B1 and the coordinate of B as A2 B2, and because the scale factor is homogeneous in the x and y direction. So, the Sx and Sy in this case is both equal to 3, which means that if I applied the geometric transformation formula here, which says that the coordinates x dash y dash becomes equal to the scale factor times the initial coordinates. Let us assume that the coordinates A1 B1 translate to A1 dash and B1 dash, and similarly A2 B2 translate to A2 dash and B2 dash. So, A1 dash B1 dash in this particular case would be represented as 3 0 0 3. Mind you, the Sx and Sy in this case are both equal to 3 times of the coordinates of A, which is A1 B1, and similarly A2 dash B2 dash should be equal to again the scale matrix here times the coordinate of B, which is A2 B2. Okay. And in other words, we have A1 dash B1 dash equals thrice of A1 thrice of B1, apply the multiplication rule in this matrix, okay. And similarly A2 dash B2 dash as thrice of A2 thrice of B2, okay. And if I were to calculate the length in this particular case, the length A dash B dash would actually be equal to root over 3A 1 minus 3A 2 square plus 3 B1 minus 3 B2 square. I am sorry, is equal to thrice root of A1 minus A2 square plus B1 minus B2 square, which is equal to AB. So, as you saw that if we use a scale factor consistent in both x and y for a single factor 3, the length gets modified to exactly 3 times in such a case. So, the scaling transformation works pretty well, and you can do this for all the sides together, which means that the intended area which is inside also gets modified to almost 9 times. So, the third transformation that we will need to understand is rotation, and by rotation what we mean is that in a 2D space, if there is a point vector, let us say v x y, and it is rotated about the origin, let us say by a certain angle theta, what is going to be the final coordinates because of such a rotation? Now, you have to remember one thing, that the rotation may or may not be along the origin, and therefore, there is a question of moving back to the origin and rotating. So, I am going to cover this in great details in the next module, but in the interest of time I will close this particular module. So, in the next module we will talk about rotation, and then we will talk about the respective 3D forms of the 2D transformations that you have visited so far. Thank you very much.